Find the Hankel transform of d square f by dx square plus 1 by x into df by dx minus n square by x square f, or prove that Hankel transform of d square f by dx square plus 1 by x into df by dx minus n square by x square into f, which is equal to minus p square f n bar of p. So we know that Hankel transform of d square f by dx square, which is equal to integral 0 to infinite d square f by dx square into x into jn of px dx. This is from the definition of Hankel transformation, which is equal to integral 0 to infinite. I am splitting d square f by dx square into d by dx of df by dx into x into jn of px into dx, which is equal to integral 0 to infinite x into jn of px into derivative of df by dx, right? Both are same, d by dx of df by dx into dx, right? So you can cancel dx, you can take like that, right? Numerator dx and denominator dx, so you will get d of df by dx into x into jn of px, which is equal to, so we are using udv formula, integral u dv, which is equal to uv minus integral v du. Here u is equal to x into jn of px and v is equal to df by dx. So integral 0 to infinite u dv can be written as uv, right? U x into jn of px into v df by dx. So lower limit 0, upper limit infinite, minus integral v du, integral 0 to infinite v df by dx into du, derivative of x into jn of px, right? So assuming that x into f of x tends to 0, as x tends to 0 and x tends to infinite, so the first term, so upper limit and lower limit, when x tends to 0 the term is 0, and when x tends to 0 the term is 0. So first term 0 when applying the upper and lower limits, minus integral 0 to infinite df by dx. We are doing the differentiation of x into jn of px, that is we are using derivative of uv, u dv plus v du, we are using that formula. So df by dx u jn of px into derivative of x dx plus x into derivative of jn of px, that is jn dash of px, and differentiation of px you will get p into dx. So therefore integral 0 to infinite d square f by dx square into x into jn of px dx, which is equal to minus integral 0 to infinite df by dx jn of px dx minus, right, integral 0 to infinite df by dx into x into jn dash of px into p dx, right? Therefore integral 0 to infinite d square f by dx square into x into jn of px dx plus integral 0 to infinite df by dx jn of px dx. We are taking the first term in the left hand side to the right hand side, right? So in the previous steps you are having in the left hand side first term minus integral 0 to infinite df by dx jn of px dx. So we are taking the term to the right hand side, so it will become plus integral 0 to infinite df by dx jn of px into dx, which is equal to minus integral 0 to infinite df by dx into x into jn dash of px into p dx, that is integral 0 to infinite d square f by dx square into x into jn of px dx plus integral 0 to infinite x into 1 by x into df by dx jn of px dx. We are multiplying and we are dividing by x into 1 by x, right, which is equal to minus integral 0 to infinite df by dx x into jn dash of px into p into dx, right. So integral 0 to infinite d square f by dx square plus 1 by x into df by dx. So we are grouping into one integral, so common term x into jn of px dx, right, which is equal to minus p is constant, so integral minus p into integral 0 to infinite df by dx x into jn dash of px dx, which is equal to minus p integral 0 to infinite x jn dash of px into df. So dx and dx in the numerator, dx in the denominator get cancelled, so you will get df. So which is equal to minus p x jn dash p of px f of x, lower limit 0, upper limit infinite. So again we are using u dv formula, integral u dv which is equal to u v minus integral v du, right. Here you are having u is nothing but x jn dash of px, v is nothing but f, right, u dv, right. So uv minus p is common, so u x jn dash of px, v f is nothing but f of x, right, f of x in lower limit 0, upper limit infinite, plus, so already you are having minus, so minus into minus plus, p is common, so plus p integral 0 to infinite, so v f of x into derivative of x jn dash of px du, right, which is equal to minus p x jn dash of px f of x integral lower limit 0, upper limit infinite, plus p into integral 0 to infinite f of x d by dx of x jn dash of px into dx, right. D of x jn dash of px can be written as d by dx of x jn dash of px into dx, so multiplying by dx and divided by dx, right. Assuming that x f of x tends to 0 as x tends to 0 and x tends to infinite, so first value, therefore integral 0 to infinite d square f by dx square plus 1 by x into df by dx x into jn of px dx, which is equal to p into integral 0 to infinite f of x d by dx x jn dash of px dx, because we are assuming x f of x tends to 0 when x is equal to 0 and x is equal to infinite. Therefore the first term when applying the lower and upper limit, both terms are 0, so we will get that first term is 0, then remaining you are having only p integral 0 to infinite f of x d by dx of x jn dash of px dx, that is equation number 1. We know jn of x satisfy the Bessel's differential equation, that is the equation is x d square y by dx square plus dy by dx plus 1 minus n square by x square into xy equal to 0, or d by dx of x dy by dx plus 1 minus n square by x square xy, right, both are same, equal to 0. So d by dx of x into, so it is satisfying the jn of x satisfying the Bessel's equation, so replace y by jn of x here, so x into derivative of jn of x by dx plus 1 minus n square by x square x into jn of x equal to 0. This implies d by dx of x derivative of jn of x is nothing but jn dash of x, right, plus 1 minus n square by x square x jn of x. Replace x by px, then dx is equal to p into dx, right. So we will get d by dx becomes p into dx, d by p into dx, so replace x by px, so px jn dash of xp plus 1 minus n square by xp square xp jn of xp equal to 0. 1 by p into p, taking that p outside, right, d by dx of x into jn dash of xp plus 1 minus n square x square p square xp jn of xp equal to 0. d by dx of x jn dash of xp plus 1 by p square minus n square by x square. We are taking 1 by p square outside. P square minus n square by x square x into p into jn of xp equal to 0. d by dx x jn dash of xp plus 1 by p square minus n square by x square x into jn of xp equal to 0. Therefore, d by dx of x jn dash of xp which is equal to minus 1 by p square minus n square by x square x into jn of xp, that is equation number 2. From 1 and 2, integral 0 to infinite d square f by dx square plus 1 by x into df by dx into x into jn of px dx, which is equal to p integral 0 to infinite f of x into minus 1 by p square minus n square by x square x jn of xp dx is equal to minus p by p integral 0 to infinite p square f of x into jn of xp dx minus integral 0 to infinite n square by x square into f of x into jn of xp dx, which is equal to minus integral 0 to infinite p square f of x into jn of xp into dx plus integral 0 to infinite n square by x square f of x into jn of xp into dx. So, integral 0 to infinite d square f by dx square plus 1 by x df by dx x into jn of px dx minus, we are taking that second term on the left hand side to the right hand side, minus integral 0 to infinite n square by x square f of x into jn of xp dx, which is equal to minus integral 0 to infinite p square f of x into jn of xp dx. Therefore, integral 0 to infinite d square f by dx square plus 1 by x into df by dx minus n square by x square f of x into jn of px dx, which is equal to minus integral 0 to infinite p square f of x into jn of xp dx. Taking p square outside, minus p square integral 0 to infinite f of x into jn of xp dx, that is minus p square f n bar of p. Therefore, Hankel transformation of d square f by dx square plus 1 by x into df by dx minus n square by x square f, which is equal to minus p square f n bar of p. So, deduction will be on the next video. Thanks.